Learning objectives. In this lesson, you will be learning about trees and the following in detail. Binary tree traversal methods. Recursive algorithms for above-mentioned traversal methods. Representation of trees and its applications. Binary search tree. Height-balanced AVL tree. B trees. Introduction. Dynamically organize data so that item insertion, deletion, and lookups are more efficient. Definition. A binary tree T is either empty or such that T has a special node called the root node. T has two sets of nodes, LT and RT, called the left subtree and right subtree of T respectively. LT and RT are binary trees. Copy tree. One useful operation on binary trees is to make an identical copy of a binary tree. A binary tree is a dynamic data structure, that is, memory for its nodes is allocated and deallocated during program execution. To make an identical copy of a binary tree, we need to create as many nodes as there are in the binary tree to be copied. Nodes must appear in the same order as they are in the original binary tree. The function copyTree, which makes a copy of a given binary tree. Binary tree traversal. The item insertion, deletion, lookup operations require that the binary tree be traversed. Common operation performed on a binary tree is to traverse the binary tree. Traversal must start at the root node because there is a pointer to the root node. In binary tree traversal, for each node we have two choices. Visit the node first, visit the subtrees first. These choices lead to three different traversals of a binary tree in order: pre-order, post-order. In-order tree traversal. In an in-order tree traversal, the binary tree is traversed as follows. Traverse the left subtree, visit the node, traverse the right subtree. In-order traversal pseudocode. This recursive algorithm takes as the input a pointer to a tree and executed in-order traversal on the tree. While doing traversal, it prints out the key of each node that is visited. Pre-order tree traversal. In a pre-order tree traversal, the binary tree is traversed as follows. Visit the node. Traverse the left subtree. Traverse the right subtree. Post-order tree traversal. In a post-order tree traversal, the binary tree is traversed as follows. Traverse the left subtree. Traverse the right subtree. Visit the node. Tree traversal example. Let's do an example first. In order: left, root, right. 3, 5, 6, 7, 10, 12, 13, 15, 16, 18, 20, 23. Pre-order: root, left, right. 15, 5, 3, 12, 10, 6, 7, 13, 16, 20, 18, 23. Post order: left, right, root. 3, 7, 6, 10, 13, 12, 5, 18, 23, 20, 16, 15. Tree traversal example. Given a tree, you are expected to know how to do the in, pre, and post order traversals. Example: write the 3 traversals of the given tree. Sorting values using in order. The in-order traversal always prints the values in sorted order from smallest to largest. One application of the in-order traversal is sorting a list. How long would it take to sort a list? Each insert operation takes O of h time, so doing n inserts would take O of nh time. The in-order traversal is O of n, so building a tree and printing its values in sorted order takes O of nh plus O of n equals O of nh time. Storing trees using pre-order. Suppose we want to transmit our tree across the country to another programmer. Sending the in-order list would tell them the values but would not communicate how the tree is built. Trees are usually stored with the pre-order traversal. All of the tree below have the in-order walk 1, 2, 3, but only one of the trees below has the pre-order walk 1, 2, 3. Binary search tree operations on BST. Searching for a key. The maximum and the minimum. Insertion. The successor and the predecessor. Deletion. Implementing binary trees. Determine whether the binary tree is empty. Search the binary tree for a particular item. Insert an item in the binary tree. Delete an item from the binary tree. Find the height of the binary tree. Find the number of nodes in the binary tree. Find the number of leaves in the binary tree. Traverse the binary tree. Copy the binary tree. Binary search trees. A special type of binary tree called a binary search tree. To visit each node in the binary tree until either the item is found or not. The entire binary tree because no criteria exists to guide our search. This case is like an arbitrary linked list where we must start our search at the first node and continue looking at each node until either the item is found or the item list is searched. Searching for a key. We assume that a key and the subtree in which the key is searched for are given as an input. We'll take the full advantage of the BST property. If the node has the key that is being searched for, then the search is over. Otherwise, the key at the current node is either strictly smaller than the key that is searched for or strictly greater than the key that is searched for. If the former is the case, then by the BST property, here k is the key that is searched for and x is the start node. BST search of x, k. 1 is to yx. 2. While y6 equals nil do. 3. If key of y equals k, then return y. Else if key of y lesser than k, then y, right of y. Else y, left of y. Return not found. The maximum and the minimum. To find the minimum, identify the leftmost node, that is the farthest node you can reach by following only left branches. To find the maximum, identify the rightmost node, that is the farthest node you can reach by following only right branches. The successor and the predecessor. The successor, respectively the predecessor, of a key K in a search tree is the smallest, respectively the largest key that belongs to the tree, and that is strictly greater than, respectively less than K. The idea for finding the successor of a given node X. If X has the right child, then successor is the minimum in the right subtree of X. Otherwise, the successor is the parent of the farthest node that can be reached from X by following only right branches backward. Search. If the item is found in the binary search tree, it returns true. Otherwise, it returns false. Because the pointer root points to the root node of the binary search tree. A pointer, say current, to traverse the binary search tree. The pointer current is initialized to root. If the binary search tree is non-empty, we first compare the search item with the info in the root node. If they are the same, we stop the search and return true. Search ends at the node containing the search item. Otherwise, the search ends at an empty subtree. Insert. After inserting an item in a binary search tree, the resulting binary tree must also be a binary search tree. To insert a new item, first we search the binary search tree and find the place where the new item is to be inserted. The search algorithm is similar to the search algorithm of the function search. Traverse the binary search tree with two pointers. A pointer, say current, to check the current node, and a pointer, say trail current, pointing to the parent of the current. Duplicate items are not allowed. Our search must end at an empty subtree. Then use the pointer trail current to insert the new item at the proper place. The item to be inserted, insert item, is passed as a parameter to the function insert. Delete. As before, first we search the binary search tree to find the node to be deleted. To help you better understand the delete operation, the function to delete an item from the binary search tree. Non-recursive binary tree traversal algorithms. The previous sections describe how to do the following. Traverse a binary tree using the in-order, pre-order, and post-order methods. Construct a binary tree. Insert an item in a binary tree. Delete an item from a binary tree. The traversal algorithms, in-order, pre-order, post-order, discussed earlier are recursive because traversing a binary tree is a fundamental operation and recursive function. Non-recursive in-order traversal. In the in-order traversal of a binary tree for each node, the left subtree is visited first, then the node, and then the right subtree. It follows that in an in-order traversal, the first node visited is the leftmost node of the binary tree. For example, in the binary tree in figure, the leftmost node is the node with info 28. Start by traversing the binary tree at the root node and then follow the left ink of each node until the left ink of a node becomes null. Back up to the parent node, visit the node, and then move to the right node. Links go only in one direction. To get back to a node, the nodes must be backtracked in the order that they were traversed. The non-recursive pre-order. The following function implements the non-recursive pre-order traversal algorithm. In a pre-order traversal of a binary tree for each node, first the node is visited, then the left subtree is visited, and then the right subtree is visited. An in-order traversal after visiting a node and before moving to the left subtree. Save a pointer to the node so that after visiting the left subtree, visit the right subtree. Non-recursive post-order traversal. In a post-order traversal of a binary tree for each node, first the left subtree is visited, then the right subtree is visited, and then the node is visited. As in the case of an in-order traversal, in a post-order traversal, the first node visited is the leftmost node of the binary tree. For each node, the left and the right subtrees are visited before visiting the node. Binary tree traversal and functions as parameters. Suppose you have stored employee data in a binary search tree, and at the end of the year, pay increases or bonuses are to be awarded to each employee. This task requires that each node in the binary search tree be visited and that the salary of each employee be updated. The preceding sections discussed various ways to traverse a binary tree. However, in these traversal algorithms, in-order, pre-order, and post-order, whenever we visited a node for simplicity and for illustration purposes, we only output the data contained in each node. How do we use a traversal algorithm to visit each node and update the data in each node? One way to do so is to first create another binary search tree in which the data in each node is updated data of the original binary search tree and then destroy the old binary search tree. The statement in line 1 declares f of parameter function 1 to be a function that takes as a parameter any void function that has one value parameter of type int. The statement in line 2 declares f of parameter function 2 to be a function that takes a parameter any void function that has one reference parameter of type element type. We can now rewrite the in-order traversal function of the class binary tree type. Alternatively, we can overload the existing in-order traversal functions. To further illustrate function overloading, we will overload the in-order traversal functions. Representations and applications. Arrays can be used to represent complete binary trees. A complete binary tree, all of the depths are full except perhaps for the deepest. At the deepest depth, the nodes are as far left as possible. There are several reasons why the array representation is convenient. The data from the root always appears in the O component of the array. Suppose that the data for a non-root appears in component I of the array, then the data for its parent is always at location I minus 1 divided by 2 using integer division. Suppose that the data for a node appears in component I of the array, then its children, if they exist, always have their data at these locations. Left child at component 2i plus 1, right child at component 2i plus 2. A class for binary tree nodes. A binary tree can be represented by its individual nodes. Each node will contain references to its left child and right child. The node also has at least one instance variable to hold some data. An entire tree is represented as a reference to the root node. Here is a demonstration of traversing trees using the above representation. Pre-order traversal, in-order traversal, post-order traversal. Pre-order traversal void pre-order, BT node root. Not all nodes have one or both children. Easiest to deal with this one also covers the case for an empty tree. Visit the root, perhaps to print it. System.out.printin of root.data. Traverse the left subtree preorder root.left. Traverse the right subtree preorder root.right. The preorder traversal of the tree above is A, B, D, E, C, F, H, I, J, G. In order traversal void in order BT node root. Not all nodes have one or both children. Easiest to deal with this one also covers the case for an empty tree. Traverse the left subtree in order of root.left. Visit the root, perhaps to print it. System.out.printin of root.data. Traverse the right subtree in order of root.write. The in-order traversal of the tree above is D, B, E, A, I, H, J, F, C, G. Example for post-order traversal. Output for the post-order traversal. A more general BT node. For a more general purpose, we can redefine the class BT node, such that each node could hold the data that is a Java object. Binary search trees. For many tasks, we need to arrange things in an order processing from smaller to larger. We can take the advantage of the order to store the elements in the nodes of a binary tree to maintain a desired order and to find elements easily. One of this kind of trees is called binary search tree. A binary search tree has the following two characteristics for every node n in the tree. Every element in n's left subtree is less or equal to the element in node n. Every element in n's right subtree is greater than the element in node n. Heaps. A heap is a binary tree where the elements are arranged in a certain order proceeding from smaller to larger. In this way, a heap is similar to a binary search tree discussed previously, but the arrangement of the elements in a heap follows rules that are different from a binary search tree. In a heap, the element contained by each node is greater than or equal to the elements of that node's children. The tree is a complete binary tree, so that every level except the deepest must contain as many nodes as possible, and at the deepest level all the nodes are as far left as possible. Trees representation. Advantages of linear representation. Simplicity. Given the location of child, say k, the location of the parent is easy to determine, k divided by 2. Disadvantages of linear representation. Additions and deletions of nodes are inefficient because of the data movements in the array. Space is wasted if the binary tree is not complete. That is, the linear representation is useful if the number of missing nodes is small. Note that linear representation of a binary tree can be implemented by means of a linked list instead of an array. For example, we can use the positional. AVL, height balanced trees. The performance of the search algorithm on a binary search tree depends on how the binary tree is built. The shape of the binary search tree depends on the data set. If the data set is sorted, this section describes a special type of binary search tree called the AVL tree, also called the height balanced tree, in which the resulting binary search is nearly balanced. AVL trees are due to the mathematicians G.M. Adelson-Velsky and E.M. Landis and are so named in their honor. The methods of building such binary trees were given by them in the year 1962. We begin by defining the following items. AVL height balanced trees. Definition. A perfectly balanced binary tree is a binary tree such that the heights of the left and right subtrees of the root are equal. The left and the right subtrees of the root are perfectly balanced binary trees. Let T be a binary tree and X be a node in T. If T is perfectly balanced, then from the definition of the perfectly balanced tree, it follows that the height of the left subtree of X is the same as the height of the right subtree of X. AVL height balanced trees. Definition. An AVL tree or height balanced tree is a binary search tree such that the heights of the left and right subtrees of the root differ by at most 1. The left and right subtrees of the root are AVL trees. Let X be a node in a binary tree. Let XL denote the height of the left subtree of X and XH denote the height of the right subtree of X. Insertion. To insert an item in an AVL tree, first we search the tree and find the place where the new item is to be inserted. Because an AVL tree is a binary search tree, to find the place for the new item, we can search the AVL tree using a search algorithm similar to the search algorithm designed for binary search trees. If the item to be inserted is already in the tree, the search ends at a non-empty subtree. Because duplicates are not allowed, in this case we can output an appropriate error message. Suppose that the item to be inserted is not in the AVL tree. Then the search ends at an empty subtree and we insert the item in that subtree. Conversion of forest into tree. A natural one-to-one relationship between the tree or forest binary tree. A forest or a tree can be uniquely corresponding to a binary tree. On the contrary, any binary tree can be uniquely corresponding to a forest or tree. Each node in the tree only up to a leftmost child, the eldest son and a right neighbor brothers. According to this relationship, it is natural to be able to convert the tree into a corresponding binary tree on each node. In addition, to retain the eldest son connection, remove the node connections with other children. Binary tree to tree. Forest conversion to convert binary tree and forest the natural way. If node X is the left child of parents Y, put X as right child, the right child of the right child, Y connection link, and finally remove the right of all parents to child connection. Converted into a binary tree. To convert into a binary tree as follows. The tree plus a connection between all neighboring brothers for each node in the tree. Just keep it between the first child node with the connection, delete the connection between it and the other children nodes. To the axis of the root node of the tree will rotate clockwise 45 degrees so that the structure is structured. Forest converted to binary. The forest is converted to a binary tree as follows. Per tree in the forest is converted into the corresponding binary tree. A binary tree does not move, beginning from the second binary tree, followed by a binary tree to the root of the root node of a binary tree as a former child nodes. When all the binary tree come together, this results the binary tree in a binary tree from the forest is converted. Binary tree or restore forest. Binary tree or forest restore process is as follows. If a node is the left child of its parent, then the right child node, the right child with the right child, both parents of this node with connections to link. Delete the original binary tree node and the right of all parents of the child node connection. Consolidation of 1, the resulting 2, 2, 3 or forest, making it clearly a hierarchy. AVL tree rotations. We now describe the reconstruction procedure called rotating the tree. There are two types of rotations, left rotation and right rotation. Suppose the rotation occurs at a node X. If it is a left rotation, then certain nodes from the right subtree of X move to its left subtree. The root of the right subtree of X becomes the new root of the reconstructed subtree. Similarly, if it is a right rotation at X, certain nodes from the left subtree of X move to its right subtree. The root of the left subtree of X becomes the new root of the reconstructed subtree. The subtree at node A is still an AVL tree, but the balance criteria is violated at the root node. We note the following in this tree. Because the tree is a binary search tree, every key in subtree T1 is smaller than the key in node A. Every key in subtree T2 is larger than the key in node A. Every key in subtree T2 is smaller than the key in node B. Therefore, we make T2 the right subtree of node A, the left subtree of node B. We make node B the right child of node A. Node A becomes the root of the reconstructed tree as shown in the figure. The dotted rectangle shows that a new item is inserted in the subtree, causing the subtree to grow in height. All keys in T3 are smaller than the key in node C. All keys in T3 are larger than the key in node B. All keys in T2 are smaller than the key in node B. All keys in T2 are larger than the key in node A. After insertion, the subtrees with root nodes A and B are still AVL trees. The balance criteria is violated at the root node C of the tree. The balance factors of node C, BF of C equals 1 and node A, BF of A equals 1 are opposite. Then the subtree with root node X requires either a single or a double rotation. Suppose that the balance factor of the node X and the balance factor of the root node of the higher subtree of X have the same sign, that is, both positive or both negative. If these balance factors are positive, make a single left rotation at X. The new item was inserted in the right subtree of X, causing the height of the right subtree to increase, the height which in turn violates the balance criteria at X. If these balance factors are negative, make a single right rotation at X. Prior to insertion, the left-right subtree of X was higher than its right subtree. The new item was inserted in the left subtree of X, causing the height of the left subtree to increase in height, which in turn violates the balance criteria at X. Suppose the balance factor of the node X and the balance factor of the higher subtree of X are opposite in sign. C++ code implementation of balance from left AVL nodes and adjust the balance factors. Deletion from AVL trees. To delete an item from an AVL tree, first we find the node containing the item to be deleted. The following 4 cases arise. Case 1. The node to be deleted is a leaf. Case 2. The node to be deleted has no right child, that is, its right subtree is empty. Case 3. The node to be deleted has no left child, that is, its left subtree is empty. Case 4. The node to be deleted has a left child and a right child. Cases 1 to 3 are easier to handle than case 4. Let us first discuss case 4. Analysis: AVL trees. Consider all possible AVL trees of height h. Let TH be an AVL tree of height h such that TH has the fewest number of nodes. Let THL denote the left subtree of TH and THR denote the right subtree of TH. B trees. The performance of the search depends on the height of the tree. In this section, we discuss B trees in which the leaves are on the same level and are not too far from the root. Definition of M-way search tree. Conclusion. Thus we learned about trees and the following in details. Binary tree traversal methods. Recursive algorithms for above-mentioned traversal methods. Representation of trees and its applications. Binary search tree. Height-balanced AVL tree. B trees.